Rechargeable battery is the most important energy storage technology for portable electronic devices and connecting intermittent renewable powers to grid and electric vehicles. Batteries are widely used in our daily life. They are consisted of one positive electrode and one negative electrode indicating their electrical potential. The electron energy in the positive electrode is lower than the electron energy in the negative electrode. Electrical energy conversion and storage can be achieved by shuffling electrons between two energy states. When we have extra energy from solar or wind power, we input the electrical energy to drive electron moving from the lower energy state to the higher energy state. When we need energy from the battery, we connect the positive and the negative side with electric load to allow high energy electron flow to the lower energy state spontaneously. Therefore, to construct a battery, we can couple one electrode with higher electrical potential and another electrode with lower electrical potential. The difference between the two electrodes is the cell voltage. But how do we know the electrode potential of each material? Does it change with reaction conditions and environment? How do we control the electrode potential of the material? In this micro-module, you will learn the governing equation describing electrode potential called Nernst equation and how to apply Nernst equation in energy conversion and storage. In each side of the battery, there is one half-cell reaction. Different half-cell reaction has a half-cell potentials. This half-cell potential determines the electrode potential of the side of the battery. Therefore, the electrode selection for battery positive electrode or negative electrode depends on the half-cell potential of the electrode reaction. Nernst equation defines the electrode potential for an electrochemical half-cell reaction from O reduced to R. Here, VO and VR are stoichiometric coefficients. The half-cell reduction potential of this reaction equals to the standard half-cell reduction potential minus RT over NF times the natural log of the product of the activity of the reduced species over the product of the activity of the oxidized species. E cell is the cell potential or electromotive force at the condition of interest. E naught is the standard cell potential. R is the universal gas constant. T is the temperature in kelvins. A is the chemical activity for the relevant species, where AR is the activity of the reduced form and AO is the activity of the oxidized form. The activity of substance, X, AX, is defined as follows. For solids, AX is defined as 1. For liquids, AX is defined as gamma X times Cx over C naught, where Cx is the concentration of X. C naught is the concentration at the standard state, 1 molar. Gamma X is the activity coefficient and is often approximated as 1. For ions, AX is defined as gamma X times Cx over C naught, where Cx is the concentration of X. C naught is the concentration at the standard state, 1 molar. Gamma X is the activity coefficient and is often approximated as 1. For gases, AX is defined as gamma X times Px over P naught, where Px is the pressure of X. P naught is the pressure at the standard state, 1 atm. Gamma X is the activity coefficient and is often approximated as 1. For water, the activity for water equals to 1 for dilute aqueous electrolytes. Here is the summary of the definition of activity for different substances. For solids, AX is defined as 1. For liquids, AX is defined as gamma X times Cx over C naught. For ions, AX is defined as gamma X times Cx over C naught. For gases, AX is defined as gamma X times Px over P naught. For water, the activity for water equals to 1 for dilute aqueous electrolytes. VO and VR are stoichiometric coefficients. F is the Faraday constant. N is the number of moles electrons transferred in the cell reaction of half reaction. Now, let's see some examples. Let's use hydrogen electrode as an example. Consider 2 protons, get 2 electrode and reduce to form hydrogen gas. How do we know the electrode potential of this reaction? What conditions we need to know to predict the electrode potential? Let's take a look. The half-cell reduction potential from proton to hydrogen equals to the standard half-cell reduction potential minus RT over 2F times the natural log of the activity of the reduced species, which is hydrogen, over the activity of the oxidized species, which is proton. Here, N equals 2 because 2 electrons are transferred in this reaction. E naught from proton to hydrogen is the standard half-cell potential of this reaction, which is defined as 0 volt. The activity of hydrogen is its partial pressure, therefore, we need to know the partial pressure of the hydrogen of the condition of interest, denote pH2. The activity of proton is its mole concentration, therefore, we need to know the concentration of the proton interest, denote CH+. The half-cell reduction potential from proton to hydrogen equals to the standard half-cell reduction potential minus RT over 2F times the natural log of the partial pressure of hydrogen over the concentration of proton. For example, if the condition of interest has partial pressure of hydrogen as 0.1 atm and the proton concentration is 2 moles and temperature is at 35 degrees Celsius, then the half-cell potential of this reaction at this condition can be determined by Nernst equation to be 0.053 volt. This means that the half-cell reaction at the condition of interest is 0.053 volt higher than the standard state 0 volt. Now, we know how to apply Nernst equation to determine the half-cell potential. We can compare the half-cell potential of each electrode reaction and select valid couples to construct a rechargeable battery. The electrode having higher half-cell reaction will serve as the positive electrode, and the electrode having lower half-cell reaction will serve as the negative electrode. The difference of the 2 half-cell potential will become the cell voltage of the battery. That's all the lesson for today. Thank you for your attention, and good luck with your equation.